Hey, everybody.
Howdy.
I must have set
Hello.
this. Hey, I, that's strange. You're all in a waiting room.
hmm
And I set this up at the beginning of the semester and we haven't had a waiting room. So I wonder if,
Dan,
what, yeah,
Zoom initiated waiting rooms for all Zoom sessions now.
automatically, I
Right.
So
can't.
this is something that's been done. Correct.
You either
It's a
have to
city.
as a waiting room or as with an ID to
Oh,
password
yeah,
catch in.
that's right.
So maybe the default is a waiting room.
Yeah, that's right. When I've been setting my other meetings up, I switched to the ID. And I don't think you even have to type it in. It's kind of automatically in the header or something, or in the link. I'm trying to figure out.
It must be because I've been in many Zoom, haven't been in a waiting room or with an ID. So I don't
Now,
know
if
how
anyone
strict.
comes late, I wonder if they will be in the meeting
Yeah,
room.
that's the problem. Yeah.
Oh yeah. Let me let's see. Yeah, Calais. I just entered her. Hey, so we are just talking. Zoom changed everything, and everyone's being put into waiting rooms. So I'll just have to kind of keep an eye on that. Yeah, here's another one. Let me just look real quick and see if I can change the settings. Okay, got rid of the waiting room. I entered a passcode. Automatically recording. I'll save. That probably won't fix this particular session, but hopefully it'll fix future sessions. We'll see. Let's see. Now I'm getting a lot of noise from one of you. I'm going to guess it's Judith. Let me find out. Yep, it was. Okay. So other than Judith, who makes a lot of background noise, how the rest of you doing? You enjoy the extra week? I made good use of it. As I was working on this grant, and it went out on Tuesday or Wednesday. I can't remember which. It was a bit of a blur. This was with I mentioned before. It's with Tim Spuck and his large team, and my part is just the afterglow piece, but it's centered in, as you know, we've introduced some compatibility, some accessibility for blind and visually impaired students. This grant would be all about that and make Afterglow kind of like 100% accessible to blind and visually impaired students. And will also pay for color combination and things like that. And actually my programmers have gotten a jump on that. The reason that the development version of Afterglow has not been pushed from Sparge yet is they're building in the color combination capability now, very generally, very broadly. So it works not just for optical, but for radio, and basically fits files with multiple layers will become usable. Anyway, so we got that done, and I was able to use the time to catch up on the videos for the overview videos for lab 3 and lab 4, and checking them, getting the points right, getting them set up in each of your sections correctly. And I think that went okay. So let's see, we've had, again, do lab 5 today, but let me give you some updates on some bugs and bug fixes. We've gotten a lot of reports, not a lot, but some reports coming from NC State. They're 1 week ahead of even us at UNC, so they're the first line of defense, and they're finding the little technological issues. So I just wanted to alert you to them, and many of them have been fixed, but others not quite yet. And Michael Allen here has been pushing ahead, and he found some bugs, not technological bugs, but procedure bugs, which is on me. And I'll explain that. I sent out an email to everyone about that, but I'll explain it as well. let me share my screen. Figure we'll go through these things just so you're aware, and then we'll jump into lab 5. Okay, I've spread you all out so I can see you. Okay, so first one was with the graphing interface. So in this lab in particular, we're going to be using the variable option, which is relative photometry and period folding. And basically in Afterglow, you'll be photometering a variable star and a reference star, and spitting those out as a comma separated value file, then uploading it here. And it had always worked for me and for most users, but a couple users it would not upload, wouldn't recognize it. And I don't fully understand it, but I guess there are subtle differences between different types of CSV files. We were being a little bit too restrictive. So we've loosened those restrictions, and that should work now as well. So pretty much any Excel file or comma separated value file should upload into the graphing tool. If it doesn't, please let me know. And also send, if you do find a bug, don't just say, hey, this didn't work. Give me as much information as you can. What was the browser? What was the operating system? If you can shoot a video, like a screencast of it not working, that helps my programmers tremendously. But that one I think is fixed now. Another one that came up is if you're doing photometry, which is again a lab 5 activity. So this came from NC State. If you're doing photometry in Safari, sometimes there's an issue where if you click on a star to get a magnitude, nothing happens. It's supposed to put a little circle around it. And this seems to be Safari specific, and it has been fixed in the Sparge version. So it has, you know, the Sparge version has been pushed. Again, that's at sparge.skynet.unc.edu. And so just tell them to go there. There's a few subtle differences, as I pointed out, I think last time, but they should be able to navigate it pretty much the same. Another bug that came up is image download. If you have an image, you have it already, and you're going to save it to your computer, it saves as like afterglow.jpg. That's what it's called, though underneath it's a PNG or something like that, or it may only be a few browsers where the name says JPG, but the browser is saving it as a PNG. We'll look into that. I don't think it's a huge issue because you can upload both JPGs and PNGs into WebAssign. It should work fine, but it might be a source of confusion, and Josh is going to track that down. Then there was one last bug that has been documented by video, though we just haven't been able to reproduce it. We don't have an answer yet. We had one student at NC State who had a whole bunch of images in their list in Afterglow and went to clear them out, you know, with the trash bucket icon to empty them all out, and they wouldn't disappear. And it is on video. It's a real thing. If you see that, please send me more information. So far, it's a one-off, and we haven't figured it out. But yeah, a bunch of technological issues cropped up over the past 2 weeks, and there's the list. Have any of you encountered anything else technologically with Skynet, or in particular Afterglow, that outside of those categories? Okay.
What I have found, I have a couple students that had in Afterglow, when we went to measurement tool,
Yeah.
they had to close Afterglow and get back in once in a while, because when you click on it and then you click to the next dot, it wouldn't be anywhere. It would be somewhere else on the picture. It's not where they expect. I had several students experience that. We closed Afterglow, started again, and it was okay.
Okay.
I've had it happen to me several times.
Yeah, I've never seen it with the measuring tool. With I think image alignment, I often see it. I go to the image alignment page or tab, and it's just messed up and everything's frozen, and I have to refresh the browser and reload the page, and then it works.
I didn't try refreshing. That might be just instead. We just closed it and opened it again, but I could try refreshing too if it happens. But
if it happens, get a video, but also try it in Sparge.
Oh, okay.
These kinds of things that require a refresh, it's often something completely different than what you're doing that caused it. And it's causing parts of the application to lock up and not behave correctly. And a refresh fixes it. Of course, we don't want that to be how the software behaves regularly. And my understanding is Josh tracked down, figured out a lot of what was causing this, and it should be fixed in Sparge. I haven't seen it in the measuring tool yet. So try it in Sparge if you encounter that. But it's one of those things that it's hard to reproduce, right? Because once you reload the browser, it works again. So we probably will only know once we switch over to Sparge and no one has any problems. Anything else? Okay. Okay, so the procedural issue. So this one's on me in lab 4. A couple things, first of all. Some of you have been waiting to do lab 4 because you want to do the parallax observation. You still can. There will be a small change in the procedure that you'll have to do. I told you 2 weeks ago that it's going to be another 1 to 2 weeks, and I'm telling you today it's going to be another 1 to 2 weeks. But global pandemics are out of my control, so don't blame me for that one. But I have been in touch with the director. I emailed him a few days ago and said, hey, we really want to get going. You said the robotic telescopes would be first. And he got back to me last night, and we're starting to put together a procedure. We don't want to just press the go, the on button and see what happens. We're going to do a visual inspection of each of the domes because wildlife can move in and move out. And we just want to have a visual inspection of each of the telescope systems first. Then we'll fire it up and run it for a night or two just to make sure it works. And then I'll let you know at that point, get back to me if you still want target of opportunity access to do the observation. Now, Michael went through the sample data, and he could only make it work on the most recent data set. The other ones failed. And the one reason for that was the older images did not have WCS. And the old procedure before the lab update using Afterglow 1, they didn't need WCS. The students did the alignments by hand with a tool that we gave them. But in Afterglow 2, we're making use of World Coordinate System and printed on the images in the headers. And Skynet adds those automatically as long as there are enough background stars, but it didn't always in the past. So the older data didn't work. We've added those WCSs as of this morning. So that data should be fine. The other issue, the procedural issue, is identification of the asteroid. I think I have lab 4 up here. Let's see, where is it? Yep, there it is.
We still see the, oh, no, never mind, sorry.
There we go. Yeah, it was behind you all on my other monitor. I found it. So the procedure for identifying the asteroid, remember the overall procedure here is we're going to observe 10 minutes simultaneously in a southern hemisphere telescope and a northern hemisphere telescope, a kind of just a rapid fire sequence on both telescopes, hoping with, we tell them don't start before, hoping that we have some overlap. As long as you're using the target of opportunity mode, it should be okay. But then you have to figure out which one is the asteroid before you can do parallax. For parallax, we align them, we stack them, and then you zoom into the asteroid and you change the brightness and contrast, and you'll see the 2 peaks there. That's the parallactic shift. But to find it, the procedure I wrote was similar. Align it, stack it, and you'll see it moving across the image. This is not going to work moving forward. The data that's in the sample directory was collected not over 10 minutes, but over hours. So here you're seeing the motion of the asteroid over the course of hours. In 10 minutes, you won't be able to see the motion. You can see it if we did it as a movie. And that's what we did in Afterglow 1. You can see one of the stars just barely inching across. But we're trying to avoid movies because blind and visually impaired students can't interpret them. So we came up with the stacking procedure where they can use sonification tools, et cetera. But in 10 minutes, you're not going to see a pattern like this. So if you collect your own data this year, or in future years, when I'm hoping everyone collects their own data, I don't want people using sample data. I really feel the students get more out of it if they collect their data, or hopefully the class as a group collecting data has a similar effect of data ownership, causing a boost in student attitudes. You know, in those cases, I'm going to rewrite this procedure to you grab an image, you load up the DSS, and you find the point that's not there. They learned how to do this back in lab 1, so it's not a new skill, and should be even easier than finding dwarf planets. So that's, I'm a little frustrated. I thought I was done, but I'll have to go back and change this procedure. But it's pretty straightforward. And if you do collect your own data once CTO comes back online, just do that. Instead of this align and stack, grab one of the images, pull up the DSS, find the object that's not in the DSS. Again, they did it with dwarf planets in lab 1. Asteroid should be brighter and easier. Now, if you're using the archival data and you use the 2018 data, you can use the procedure as described. That's what we're looking at here, just because in this case, the data was collected over multiple hours. So it does work in that case. Well, so that's that, the little hiccup there. But if you do lab
Dan?
4, yeah, go ahead.
You said the spring of 2018, correct?
Spring of 2018. Yep, that
Okay,
data set
thank
will
you.
work with the current procedure. But we'll get that fixed up. Changing the text, you know, it'll only take me a day to change the text and maybe reshoot a video, but getting it processed and encoded by WebAssign takes time. So don't expect it in time this semester, but it will be in place by next semester. Okay, let's move on to lab 5. I like this lab. We're continuing to move along the cosmic distance ladder. In lab 4, we of course did parallax, which gets you, actually, let me bring up the little upside down pyramid chart, just to remind us where we're at. So in lab 4, we did Earth baseline parallax, we did stellar parallax, that's gotten us out to nearby stars. Now we're going to do standard candles, our Lyraes, Cepheids, type 1As to get farther and farther out. The stellar parallax can now get you about halfway across the galaxy thanks to Gaia. There used to be an intermediate step here, spectroscopic parallax, that you'd have to do before standard candles. And I know, when I wrote this back in 2008, I knew Gaia was coming, and so I cut that out prematurely just to kind of streamline the cosmic distance ladder for the students. And now guys come along and spectroscopic parallax is not really a deal anymore. So you can go straight from stellar parallax to the Lyraes. They, of course, make it, we can use them across the entire Milky Way and out to the globular clusters. And then the Cepheids we can use out to nearby galaxies. And in the next lab, we'll use both of those again. So this lab, we're going to learn the techniques and measure distances farther and farther out. Then lab 6, they'll use these to redo the great debate of 1920, using our Lyraes to find our place in the Milky Way, and using Cepheids to show that the spiral nebulae are galaxies in their own right, like our own. So 5 and 6 kind of go together. And then we'll also do a type 1A, which ties into the cosmology lab, lab 8. Okay, so that's just an overview here. Yeah, so lab 5. Again, I have to shoot a new video. This is the old video, and I'll update the instructions, but there will be an observation for lab 6. And so remember to tell your students to put this in. And this one is very straightforward. You go to lab 6, procedure section B, part 1, and they're just going to observe some spiral nebulae, some galaxies, just single images, single 80-second images, something they've already done before. So not very complicated, but they'll want to put them in advance. Okay, let's dive into it here. Goals, I've already told you, to use our Lyraes to measure distances within the Milky Way, Cepheids to nearby galaxies, type 1A to faraway galaxies. Equipment is just the computer. We have a couple background sections. One introducing the concept of magnitudes, which we haven't used yet in the course, both apparent and absolute. Well, apparent anyway in this section. Standard candles, where we'll introduce the idea of, an object of known luminosity. You measure the brightness, you calculate the distance, but also in terms of apparent and absolute magnitudes. And then in background section C, we'll talk about these two variable stars in very simple terms, and section D, type 1a supernovae in very simple terms. And the R-Lyri, that will be data that you collect as a class. And you can do that this semester as well. There is sample data, but again, I'm going to encourage you to collect your own, and I'll describe that as well. But the Cepheid and the type 1a, that's archival. Because the Cepheid takes 60 days to collect that data for just one period. That's too long for the students to do. And the type 1a supernovae, you never know when they're going to go off. So those will be archival. Okay, let's go into the background sections. And again, I always feel silly going through the background sections because you know all this stuff, you teach all this stuff, but I'll just kind of run through it quickly as you might to a student. First, we introduce the idea of apparent magnitude and point out that often that's just referred to as magnitude. If someone says magnitude, they mean apparent magnitude, and what we're talking about is brightness. And you'll notice throughout this lab, wherever I say magnitude or apparent magnitude, I usually say in parentheses, think brightness. Wherever I say absolute magnitude, I usually say think luminosity. Constantly drill in those connections there. But here we are with apparent magnitude, just a few standard objects, and pointing out that it's a reverse powers of 10 scale.
I'm going to interrupt for a second, Dan. There's a chat you might want to read.
Yes. Let me find that here. Do I have someone in the waiting room? Is that it? Trying to figure out how to, where is that?
Look at the participant list.
Oh yeah, it's right. Dave Moffat. Yep. I assume that's what the chat message was, Dave, not adding Dave to the room. Okay. Dave, you here now? I think I added him. Oh, and now we have Enrique. I just added him. Okay, Enrique, you've been added. Dave Moffat. There he is. Yep. Sorry. Zoom, when they did their update, they changed things, and so now everyone's being dumped in a waiting room. I've fixed it for next time, but I'll try to keep an eye on it this time. Okay.
Thanks.
So you may have been there for a while because I haven't checked for about 5 or 10 minutes, so I apologize. Okay, so introduce the concept of apparent magnitudes, and then we're going to teach them how to do manual photometry. We go through the manual exercise once because later down in the lab, it's batch photometry where they'll be doing scores of images simultaneously, and that's kind of black boxish. So we want them to go through it manually once. There's a tutorial how to do this, but I'll just show you right now. So we're going to go to Afterglow, and there's a file in the sample directory under CD47. It's a calibration field. I'll import it. And in the lab, we provide a finder chart. It looks like I've already marked it here. Let me get rid of these so I can show you. Okay, so here's the field, and here's the finder chart. And so they have to find star A and the reference star. So star A is going to be this one right here. The reference star is going to be that one right there. Sometimes students may have a little difficulty because the finder charts are black on white and the images are white on black. So sometimes it helps to invert them when comparing to the finder chart. But zooming in here, nope, wrong lab. Let me just get rid of that so I don't click on it again. Yeah, so this one, right? Just want to make sure. Yep, that's star A. Here's our reference star. So we're going to go to the photometry tool. It's the one over here with the star. And everything should be turned on, centroid clicks in particular. And so I'm going to click on it, and it adds it, and it takes a second, and it does the photometry. So it's hitting the server to do the photometry. That's why there's a little bit of a delay. And I've forgotten already, but I'm pretty sure that this one right here is the reference star. So we just added that, and there's its photometric value. And so you can read the magnitudes off of there. Going back to the lab, they put their magnitude for star A here and for the reference star here. But we point out that if they were to come back and take this image on another day or even another time on the same day, they would get different magnitudes because maybe you're looking through more atmosphere, or maybe clouds have come over. So these magnitudes, these brightness measurements mean nothing unless they're calibrated. That's what the reference star is for. The reference star is a star of known apparent magnitude, and we give it here. These are V-band images, and so in the V-band, it's 12.02. And so they calculate a correction constant, the true magnitude 12.02 minus the uncalibrated magnitude of the reference star. They get a correction constant here, which they then add to their uncalibrated magnitude of star A to get a calibrated magnitude. So they're learning how to photometer something, but also how to calibrate it. And it's tricky because calibration, we all know it's super, super important, but it's also one of the hardest things to explain to students. And they don't understand why they need to calibrate their data. So they're walked through it here. And then you'll see it in batch mode, but it's a little bit more subtle in batch mode. So again, that's why we do it manually in one of these background sections. Okay, standard candles. We start with this equation, which they may be familiar with. Brightness is luminosity divided by 4 pi distance squared, or which you can then solve for distance as such. And the idea is if you have an object out there of known luminosity, then all you have to do is measure the brightness. Measuring brightness is the easiest thing to do. In astronomy, that's what we just did. We just measured the brightness or the apparent magnitude of a star. But just because a star is out there doesn't mean you know its luminosity. You can't tell its luminosity by looking at it. But we, of course, there are certain types of objects out there that if we can say, oh yeah, this is this type of object, then we know its luminosity. And we know that because there are some of them close enough that we measured their distance with parallax. And I do go through this process. How do we know? How do we bootstrap our way up throughout the lab here? So there are some of these stars, let's say our Lyrae stars, they were close enough that we can measure their distance with parallax, measure their brightness, and hence calculate their luminosity. And after studying all of them as a class, we realize, oh, they all have the same luminosity. So we can then flip that around. We can find ones farther out and say, oh, that's an R Lyrae star. It has a luminosity of such and such. All we have to do is measure the brightness to get the distance. That's the idea. Now, since they're using magnitudes, they're going to be using this form of the equation and may look a little different than what you're used to. And normally it'd be 0.01 kiloparsecs times 10 to the little m minus big M over 5. But I learned just from doing this with hundreds of survey students, they make so many calculator errors there. They do 10 to the m minus m, then whole thing divided by 5. They do 10 to the m, enter, minus big M divided by 5, all sorts of calculator errors. So as I present in the lab, I've done 10 to the 1/5 for them. That's what the 1.585, and that's why it may look a little different from what you're used to, but it does solve a lot of calculator errors from students, and it goes more smoothly. So this is the equation we give them, and we don't do a derivation. That's a little bit more than they would need here, but we tell them that this is equivalent to this. Here's your brightness, luminosity, distance equation. This is the same thing, just using little m for brightness, apparent magnitude, and using big M, the absolute magnitude, for luminosity. And I don't know if we even define absolute magnitude in the lab. In my lecture course, I certainly do. That, an absolute magnitude is the apparent magnitude it would have if the object were at 10 parsecs. Here, I think we just keep it simple and say it's analogous to luminosity. Okay, that's the background section on standard candles, and then we look at the standard candles we'll be using. The first are variable stars of two different types, are Lyraes and Cepheids. And there are two types of Cepheids. I don't get into that here. I'm using the type that I should be using. I forget if it's type 1 or type 2. And if you know out there which one I'm actually using here, anyway, it's the one I should be using. And the simple distinction is there are Lyraes, they vary with the time scale of less than a day, the Cepheids more than a day. Now, why are they varying? And I also try to keep this pretty simple here. In Astro 102, my Stars, Galaxies, Cosmology course, I go into it in more detail. Here I just say the outer layers are stably unstable. They get bigger and smaller and bigger and smaller. What's really going on are opacity differences. The gas becomes opaque, and so it traps heat and expands. And then it's lower density, the opacity changes, it releases the heat and contracts. And so it's that kind of cycle. But I don't get into that in this because, again, it's survey level. They may not even understand the concept of opacity independent of the lab course. They're just stably unstable outer layers that oscillate, and we can use that to identify them. And again, by looking at nearby ones where we can measure the distance using parallax, we learned that all the Lyraes, they have the same absolute magnitude of 0.75, corresponds to about 50 solar luminosities. And with the Cepheids, they don't all have the same absolute magnitude or luminosity, but it is a function of their period. So if you can find a Cepheid, you have to measure the period anyway to know whether it's an R-Lyrae or a Cepheid. Once you have that period, you can plug it into this equation and get the absolute magnitude for it. And so the 0.75 is going to be very important. This equation is going to be very important in this lab and the next lab where we do the great debate. Now they may not have great familiarity with logarithms, and it's okay. It's just a calculator button for, if they don't understand it, they don't really need to. We tell them make sure that they're using the base 10 logarithm. Okay, and then for the type 1a supernovae, we tell them a little bit about the process here. You have two stars in close proximity. The more massive one comes to the end of its life first. Remember, with my students anyway, it's mostly solar system students who are taking this lab. Only a small fraction go on to 102. So this is their taste of the rest of the universe. So I do try to explain a little bit, but I also recognize that they're not in 102 and I'm not going to explain it in great depth. But anyway, two stars in close proximity, one's more massive and comes to the end of its life, forms a white dwarf. The other one then enters the giant phase and transfers mass over onto the white dwarf, making it more and more massive. Eventually, it hits the Chandrasekhar mass where it can't hold itself up anymore. In reality, it will go through a series of nova explosions. You dump material on the surface, and once you have a critical amount, it explodes, burning hydrogen into helium, but that helium, for the most part, sits there. And so you have nova after nova after nova, and it gets more and more massive until it hits that Chandrasekhar mass. I don't go through the nova explanation here. And then it can't hold itself up anymore, so it begins to collapse. And a common misconception is it collapses down to a neutron star, and that's not the case. If it were made of pure iron, yeah, that's what would happen. But this is made of carbon and oxygen. So as it collapses, it heats up, it hits that carbon ignition temperature, and then the whole thing ignites. And there's all sorts of debates. Is it a detonation or a deflagration, like a fast explosion or a slow burn? And in reality, it could be a combination of both. that's cutting edge. We don't need to have that in here. The idea is it's 1.4 solar masses. It always blows up with the same amount of fuel, so that's why it's a standard candle. You have the same type of explosion because you're burning the same amount of material. And the type 1As, they can be distinguished from their light curve. Here, I think I'm just referring to them. No, I do refer to it as a type 1A. You have type 1Bs and 1Cs also, but they're pretty much the same as type 2s. These are massive stars exploding on their own, a very different process. But the 1As, that's the white dwarf hitting the Chandrasekhar mass, and they have different light curves. The type 2s, as they're expanding, you have this shell that's getting brighter because it's getting bigger, and you have this plateau phase. But if it peaks and then just drops, you know you have a type 1A, and then you can use it as a standard candle. The type 2s are not good standard candles. Anyway, a bunch of these have occurred. They were in galaxies that we measured their distance to using the Cepheids, and we learned that they all have the same peak absolute magnitude, minus 19.3, at least approximately. There are small differences, which have resulted in Nobel Prizes, right? The small differences, that when the peak occurs, it can be a little bit later and a little bit fainter, and figuring out that correlation, you can make this into an even better standard candle. We're not going to take it to that level in this lab, but they can be made even better and then hence used as a probe of cosmology, which we cycle back to in Lab 8.
Dan, someone's still trying to get in and being asked for a password. Dr. Kulkarni, I guess.
So she needs the password. Okay. How do you all know this if they can't get in? Are they sending a general email? Is that it?
I don't know.
Yeah, he sent me the email and CC'd me the same email to me.
Okay, so the passcode for this, I got it right here. Normally just clicking on the link will do it.
I never got a link. I had to go to the calendar link that you sent, and it had the passcode in it.
Right, because you all have the old link before they changed Zoom. Okay, let me just go to my email real quick. It's over here.
Okay, thanks.
I'm just going to send it to the whole list to mitigate this. Okay. Okay, good. So yeah, there we go. So let's start going through the procedure parts of the lab. And I've lost you all. There you are. Okay. So first is the observation. And this, again, you'll want to put this in a week ahead of time. This is also a group observation. The parallax one's a group observation because it requires that special target of opportunity priority level that we can't give to everybody. This one's a group observation because it eats up a lot of time. So instead of giving the students all that extra time to burn through, we're going to do it once per class. And we have 3 targets. These are all Southern Hemisphere targets. You kind of really need to have quality images here. I tried to do this over the summer where most of the telescopes were down and I had to use whatever was available. And if you have a lower quality telescope requiring a longer exposure time, you can get streaks and then the photometry is not as good and it didn't work out as well. So the instructions are written to use the Southern Hemisphere prompt telescopes. Currently there's 1, but soon there are about to be a whole bunch of them.
And could I ask a quick question? This is Enrique.
Yeah, go ahead, please.
Yeah, it's for Afterglow 2. What is the photometry algorithm that's running in the backend? Are you using aperture photometry or things
Yes, it
like
is.
that?
It's aperture.
Okay, and so can you use it in crowded fields like for like I'm looking at globular clusters, right? Is it something that you can successfully use there, or are you picking up RLREs that are kind of like substantial distance away from the crowded part of
That's
the
right. These are in the outskirts. I haven't done a thorough testing of how well it works in the central region. Eventually, someone's going to try to do an HR diagram lab. In fact, that was built into our second proposal that wasn't funded because we opted to take the bigger proposal. So, it was our plan to do an HR diagram, in which case we may have to upgrade our photometric technique from aperture to something a little bit fancier. But in this lab, we chose them in the outskirts. Okay. So we have 3 targets, one for each semester. We have Northern Hemisphere fall here, and then one for Northern Hemisphere spring, and then one for the summer. The videos, I use the summer example because you have the fewest students doing that one. I don't want to like do it for them in the video. So the videos use the summer example. We'll use this one here. I'll show you real quick how to put that observation in.
Might want to check the waiting room, Dan.
Yep. Admit all. Right. I sent the link, but that just puts them in the waiting room. Hi, everybody. Welcome. Sorry for the problems. Zoom changed how they're doing things and it messed with the settings. So I'll have it fixed up for next time.
Yeah, sorry about that. Sorry to interrupt you.
No problem at all. Okay, so how to put it, let me show you quickly how to put the observation in. It's very straightforward. We got Skynet, optical observing. Again, there's a tutorial linked in the lab how to do this. Add a new observation. We're going to do the Northern Hemisphere fall one, which is NGGC 1261. Found it. Make sure this is -12, 20, and 0.5. Don't need the advanced settings. It's clearly a Southern Hemisphere object. Those are my Southern Hemisphere observatories. Choose the filter. And this one has to be done, I'm checking the lab right now, it has to be done in the V band because we're calibrating. And so that has to be done in a filter. You can't just do high throughput luminous. Okay, so V band's already selected. That ruled out a couple of the telescopes down there, but not a problem. Save and continue. And as we just talked about, use the prompt telescopes. The RCOP one just leads to streaky stars and bad photometry for this particular exercise. So I selected those. Right now, you don't see the ones in Chile, but as soon as they come back online, I'll add them to your time account. And for the generic system, we're going to do 50 80-second exposures. And you can see how the exposure time scales for these other telescopes. And then here's the only difference, and it's the same thing we did in lab 3. It's a monitoring observation. We're going to repeat this observation 50 times with 1 hour between each. You make sure that you can continue on next available telescope if interrupted. That should be clicked by default. In case the telescope goes down, you want it to switch to another one to continue. Save and continue. And time account does not have the required number. Oh, my bad. I screwed this up. Sorry. Don't listen to me. 1 exposure, 80 seconds, and we're going to repeat it 50 times. I just told it to do 50 exposures, repeating 50 times. That's why I didn't have enough time. Let's try to submit that. Okay. So I'll let that go through. I'll start collecting a sample here. Okay. That's how to put it in. And again, you want to do this the week before, and it's best if you do it in front of your students if you can. If you're in person or synchronous, do it in front of them so they feel part of it. So they feel it's like their observation. It's a class observation. And this is the only other one we do at the class level. Everything else they'll get themselves. You select, it's important that they select which globular cluster they're using because that determines all the auto grading. If they select the wrong one, they'll get a lot of points marked incorrectly. Now we're going to determine the distance to the globular cluster, and then we'll repeat this for the Cepheid and the type 1a, but it's the same thing 3 times in a row. It's repetition, but good repetition. Like with the parallax, we did the parallax exercise 3 times. It reinforces in a good way, I believe. Again, there's a tutorial on how to do this. Let's just go to Afterglow. Empty this out. And I'm going to grab data from the sample directory, but hopefully you'll be going into group. You'll send your students through your group's observations and tell them where to find the data. But right now I'm just going to grab one from the sample directory. And what was it? 1261. Select them all and import. It may take a minute to get them all in there. Oops, I clicked on something I didn't mean to. Delete that. Okay, and in the lab, we provide a finding chart. They're up here, and I actually have all sorts of different flips and orientations because students sometimes have a really tough time with that. So that's one of the improvements we made. And so I'll try to match this up with one of these, and I'm looking at it off screen, but it is clearly this one. So by looking at the finder chart, this is the R-Lyrae. I'm in photometry mode. This is the reference star. And now that I've selected these, I'm in sky coordinate mode, which means I'm using the WCS. I have the centroid clicks. You want to make sure these are all on. I measured those magnitudes, but now if I go to any other image, it's marked in those images as well. If I go down here, we may even have a flip. Anyway, it automatically finds them in all of them. And so I'm going to select them, and I'm going to click this box here, which selects all the images. I'm going to photometer all of these images simultaneously. Press the photometry button. It's done as a job, but it just photometered 2 sources and 44 files. I'm going to download it. And I didn't mean to open it. I don't need that. I just need to know the number, the name of it.
Dan, I'm sure you said this before. I must have missed it. How does it know M16 is the reference and M15 is the target?
Oh, it does not know. I clicked one and I clicked another, and it just I don't know why Josh chose this, but as I keep adding sources, it just keeps adding M's, M17, M18. Oh, but the user knows because it's labeled in the finder chart. That's the R-Lyrae, that's the reference. And so once they find it, it was this one right here. They say, okay, that's the R-Lyrae, that's the reference. They find it in their image and they click, and they'll just have to remember that this first one was the R-Lyrae, the second one is the reference.
No, but how does it do differential photometry without knowing which one is which?
Well, you'll tell it to. So once that's the next thing. So that's
I see. It gives
perfectly timed.
Okay, got it.
Now we will eventually be building this kind of light curve relative photometry periodogram stuff into Afterglow. But right now it sits with the other graphing utilities. I'm going to bring in the data file. It's in my download directory. It was called Afterglow Photometry. I was trying to get the number, but it's probably this one right here. Open it. Okay. So we have our photometry here. So we're going to select variable star. This answers your question. 15 was the variable star. So it automatically subtracts the second. You can see what's going on here. We have the variable star plus the correction constant that they learned about in the background section. You type in the actual magnitude here of the reference star, and that's included with the finder chart. And I've corrected this for dust along the line of sight already, so they don't have to worry about that if they were to even think of it. 13.87, type that here.
So underneath.
Say again?
Dan, I had a question for you real quickly.
Yeah, go ahead.
That is, how was the reference star selected? was the reference star selected? Is this from the AAVSO or is it something from a standard field?
It's been so long, I can't remember. We picked these in 2008. I think it was selected just to be something relatively close to the reference star, and all of these are close to the R Lyrae. So you find the R Lyrae, and the reference star is something that's relatively bright, relatively nearby. And the photometry, I'm sure we got from either it's a standard field or AAVSO. I'm sure I tasked my postdoc at the time to get me the magnitudes, and he probably did the dust correction himself. So I'm not exactly sure where he got it. It may predate AAVSO. I'm trying to remember, because the Southern Hemisphere AAVSO telescope was at prompt. I just can't remember when they finished up.
Is the dust correction something that is in the lab? Do you talk to them about, or just you
No,
accept it?
I don't think I mention it. I might. I'm actually not sure. I might mention it in the lab, but just offhand. Again, this is survey level. Most of these are non-majors. It's probably something they're not going to think about. Okay, and so I selected the reference star. I put in the reference star magnitude, and you can see what we've plotted here. Variable star magnitude plus correction constant. The correction constant is the true minus the measured magnitude of the reference star. And as I typed it in, it updated the numbers here. You can see the numbers change on the y-axis as I type that in. Then the next thing we need is to figure out the period. This is oscillating on a time scale of less than a day, but we're only getting data on parts of days. And in the lab, there's a link to a video on period folding that explains it really well, done by my former postdoc. I won't go through it now, but it's worth a watch, showing that this is what originally is like, but then throughout the daytime periods and then bad weather and this and that, and what you're left with is something like this, that maybe it's oscillating, I don't know. So what is the period? You could go to period folding and try different things, 0.1 days, 0.2 days, 0.3 days. You'll never find it because it's really, really sensitive. So you go to the periodogram. This is like a Fourier transform. Fourier transforms have to be done on uniformly spaced data, and this is not uniformly spaced. So you use a Lom-Scargill transform, but they don't need to know what any of that is. If you're working with more advanced students, there's all sorts of good things you can do here, particularly once we start analyzing pulsar data using this kind of tool. They just have to find the highest point in the periodogram, and it tells them 0.3318, something around 0.33. So then go to period folding and try 0.33, and that looks pretty good. And you may fine tune it, 331, 332. You can see it's getting worse. Let's go back to 3.3, maybe 2.9, 2.8, 2.7. No, that's getting worse. It's probably 0.330.
Is there a chi-squared measurement for these things, or not quite?
Not quite. With periodograms, you can draw a line of like 1 sigma, 2 sigma, 3 sigma significance. That might be something that's good to add for more advanced students, or add it as a button. So you can see like this stuff's below the noise, don't take it seriously, but anything above this or above this or whatever, these are real peaks, real signatures.
So Dan, I have a question.
Yeah, please.
When we did the moons of Jupiter and the moons of the other ones, why didn't you use the same tool for finding the period?
That's not a bad idea. So we used this modeling tool for that, but you could
how else do you know the period if it's like IO or something,
right?
Like
well,
yeah,
with IO it would be very hard. Now in the lab we pick things with a period. Each planet has one particular moon. We tell them which one to use, and it has a period between 1 and 2 weeks. So if they're collecting data pretty much daily, they should be able to see it. And
But you could do them all with the periogram, right?
you could do all of them with the periodogram. You stick it in there, give you the period. You'd still then need to come back.
Yeah,
and
you still come
figure out-
back and fit it. Yeah.
Yeah. But yeah, you definitely could. You could do tougher cases. Again, I'm targeting those student, it's survey level where most of them are non-majors. So I'm trying to simplify it as much as possible. But I
Right,
understand
but
this-
later,
Yeah.
later they'll be using the periogram, so it might be a good way to teach them how to use it.
Yeah, to introduce it here. That's a good idea. I'm going to write it down. Because one thing we do tell them, if you're having a hard time, go look up the period on Wikipedia. Because sometimes, even with the long period ones, if their data is too sparse, they can have a hard time. Like even with this one, sometimes I get it right away, or sometimes it takes me a few minutes to line it up.
I won't do that because it messes with my philosophical measurement concepts. I mean, they have to measure it themselves.
Right. Yeah. But they could, you just have to put it in, if you want to use this, well, we have a table here too. You don't need the data upload. You could have Julian date, and you could enter the distances here under source magnitude, leave these zeros, and it will work for you. Yeah, that's great. Okay. And so, though when I left, I lost all my data, but you saw, I won't go through it again for time. I'll just show you where we were. So this is answer key mode, but you can see them. And it plots 2 cycles, and that's standard when doing period folding. And of course, they also will need to put in the an appropriate label and axis, title and axis labels. But that's explained in the video tutorial, and you've seen how to do that using these boxes down here. Now back to the lab.
So Dan, good
Yes.
question. So is it completely left up to the student how many exposures they'll take and how many samplings they'll get?
So you were stuck in the waiting room. You missed this.
Yeah, sorry about that. Yeah.
No, that's okay. This is the other group observation. The parallax in lab 4 and the R library in lab 5. You do one observation for the whole class, just because this eats up a lot of time. It's 50 exposures with 1 hour gaps between them.
Right.
If every student did that, we'd have to give a lot more telescope time and be trickier. So you, the instructor, will put this in front of them so they see it and feel part of the process.
Okay.
But to walk you through, once they've done it, it says, what's the period? And they put it there. Is this consistent with being an R library? It's less than a day. So the answer is yes. What's the average absolute magnitude? That's from the background section. All R libraries, it's 0.75. What's the average apparent magnitude? So they go to their plot, and it's halfway between the peak and the trough. And they can just read it off here. Like the one we were doing was this one. And so it would be about 16.7. And so that goes here. They calculate the distance. Again, that's this equation given in the background section. Show their work. Look up the true distance in kiloparsecs and calculate a % error and discuss significant sources of error. Primarily being that it's kind of noisy. It's hard to figure out the peak and the trough. And so the halfway point is a bit of an estimate. And also the absolute magnitude is 0.75, but it's only approximately 0.75. Some R libraries are a little bit higher, some are a little bit lower. So they go through that process. They've measured the distance to an R library, and now we're going to repeat it for a Cepheid. And this is a Cepheid in a nearby galaxy. It's actually the only one you can do with the prompt telescopes, if you want to get out of the local group. And it's a 60-day period, so that will be done archivally. And since we're at noon, I won't go through it, but it's exactly what I just showed you. You load them all in. They identify the reference, the Cepheid and the reference star, batch photometer, all of them, download the Excel file, put it up in the graphing utility, and go through the same procedure. They'll measure a period of about 60 7 days. So you can see what it looks like, the folded light curve. And same questions. Is this consistent with being a Cepheid? Yes, that means we can use it as a standard candle. What is the absolute magnitude? Well, for Cepheids, it depends on the period. Again, there's that equation from the background section. They'll calculate it this time instead of just entering a constant like with the Aralaries. What's half the distance between the peak and the trough? In this case, it's about 17. That goes here. Calculate the distance, look up the true distance, percent error, sources of error. And then you have the faraway galaxy. And this one, again, I apologize for going over. This one does have one extra different step. They need to figure out the supernova themselves. So this is a type 1a supernova discovered with prompt some time ago, where the leading discoverer in the Southern Hemisphere, or have been for many years, maybe not still, but for a run there, we were the leading discoverer of supernovae in the Southern Hemisphere. So we give them an archival data set because we never know when these are going to occur. And we give them the reference star. And we're telling them to figure out which one is the supernova. We give them a hint. It's close to the galaxy. So, it's this one right here. We walk them through the process. We used to do it with a movie, but again, we're avoiding movies. So we have a new procedure to identify using image subtraction. Let me just show you that really quick. So I'm going to go to Afterglow. Let me clear these out. And this is how supernova hunters do it. They do image subtraction. So I'm going to go to the sample directory, and it's under Faraway Galaxy. And it's actually there twice. The one under supernova is kind of the raw data. The one under Faraway Galaxy, we've removed hot pixels so they don't get distracted and zero in on the wrong thing. Let's load these in. Okay, and so let me clear out these photometric measurements because somehow remembered what I was working on before. So we're going to take the first one and the last one, and we're going to align them and subtract them. So let's go to the aligning tool, and here's that little bug that I was telling you about. It's been fixed in the Sparge version. I have to refresh my browser there. Okay, images to align. I'm going to pick the first one. I'm going to pick the last one. Submit. Okay, they are now aligned. Then I'm going to go to the image calculator, one step above. I'm going to select that first image, subtract the last image. And this works if you have roughly the same number of counts coming into the images. To do it carefully, you would have to calibrate both before you subtract, but it works out fine here. So we skip that step for these introductory students. And I'm going to submit. And it's created a new file that's the difference. You can see it here. And so the stuff on the edge is just because the two weren't lined up perfectly, but all the stars, everything's canceled out, and you're looking, and it's pretty apparent this is the supernova. Now there may be little residues of other stars, imperfect cancellations, because the alignment wasn't perfect. You get a little bit of bright and dark next to each other, but this is pretty clear. And so what you do then is we're going to split the screen. And in the second screen, we'll load in that first image, and we're going to sync them. So the screen splitting, the syncing, that's all under the gear item. And so you zoom into the object you found in the difference image. And so it's clearly this one right here. And they're going to mark it, label it, and then they're going to download both the difference image and the true image into the lab here and here. And then they do photometry on the supernova and the reference star, just like we did with the R Lyrae and the Cepheid. Since I'm running over, I won't run through it. And they load it into the graphing tool. They just won't do the period folding. They'll just, use that light curve, that first plot in the graphing tool, the light curve function. They'll select one of it as the supernova and the other is the reference star. And if I didn't point it out before, these are running upside down since the magnitudes go backwards. And so the peak will be up at the top. And they'll calibrate it in the lab. We give the magnitude of the reference star. And so this appears to be about 14.6 magnitudes. And then you have the same questions. Is this light curve consistent with the type 1A? There's no plateau as we saw in the background section, so it's a 1A. What is the absolute magnitude of the peak? Again, in the background section, all type 1As minus 19.3. What's the apparent magnitude of the peak? They read it off the plot, calculate the distance, show their work. We give them the true distance to this one, 56,000 kiloparsecs. They calculate percent error, and sources of error the same as before. So basically the same thing 3 times, just a little twist on the last one. They have to identify the supernova. Okay, so I will stop screen sharing. And sorry, that came out a little haphazard, me with the waiting room and everything. And I had lots of distractions, but I hope I got everything across there.
Dan, I have a quick question.
Yeah.
Well, maybe not so quick, but supernova surveys are now reliably identifying fairly often type 1As between magnitudes of like 13 going down to like 17 or something like that. How easy would it be to adapt this instead of using archival data to just adapt it to say it's like, hey, there's a sufficiently convenient type 1A supernova. Here's the field, here's the reference star. Go ahead and just use that as opposed to using the archival data.
Yeah, I think that's doable, particularly since we're adding this new feature where you'll be able to upload data from other sources. And we do have a supernova search program on the prompt telescopes as well. So we could go either way. You could have some external supplier of type 1A data and upload it, or we can partner up with the DLT-40 survey. They're finding these things using our telescopes, using prompt telescopes, and just figure out which is the most recent and put it in there.
Could I just go to the Rochester supernova page and say it's like, hey, there's a type 1A magnitude 14. Let's go and get it.
Yeah, I think you can. And you'll need to, have a reference star and know the magnitude of the reference star. And don't worry about the dust correction. That's just it's a minor thing, right? We are building automatic image calibration into Afterglow. So, that may be one approach there for getting that, the reference star magnitude. Trying to think what else. The subtlety, so where it could go wrong is if the supernova is right smack in the galaxy. In this particular example, it's out in the outskirts, so we can still do the aperture photometry. Otherwise, you're going to have to difference everything and do the photometry on the, you'll have to make sure that your last image was sufficiently light that the supernova is completely gone. Then you get the difference images and you do the photometry on the difference images. But it should be easily generalizable. But there's also that one extra step where before doing the subtraction, we'll have to calibrate each frame. This one just worked out because the first and last image have pretty much the same calibration level. So we kept it really simple for the survey students, trying to minimize the steps, but I think it could be generalized for slightly more advanced students pretty easily.
Presumably you could divide instead of subtracting 2 images. And
yes.
That would save calibration.
You were correct. Yeah, let me write that down too. I'll have to play. I'm trying to think if there are any other subtleties that may come up.
The only other issue with dividing is that whatever's in the denominator, the noise is going to amplify.
Yeah, I was thinking, what if I had some bad negative pixels? It may be distracting. But hell, I mean, let's just do it right now if you want to stick around for a second. We can divide those two images and see what it looks like.
But the other thing you can do is subtract off the median of the two because they're both of the same basic view of the world.
Mm-hmm.
And then subtract, or divide out the median and then subtract.
Okay, so image arithmetic. Slide you all over just a little bit farther. Image arithmetic, I've already aligned them. So I'm just going to change this to divide and we'll see what happens. Submit. Okay, something did not go well there. So I'll have to figure out. Oh, no, there is stuff here. I see, you probably don't see it, but there are a few pixels here, zooming in here. So I think it did it. It just, a few pixels are dominating the dynamic range of the image. If I come up here, yeah, see how the histogram is? So if I were to, I'm not sure which way I need to go. Yeah, we have a few pixels that are messing with the dynamic range. If I were to pick the lower and higher levels appropriately, I could probably get what we want. But
and also look at it logarithmically.
Yeah. Yeah, we just sent a couple pixels that are just ruining it even logarithmically. Anyway, it's certainly worthy of further exploration. Oh, I'm still sharing. 1 second. There we go. Okay. Any other thoughts or ideas?
And these are all images taken in rapid succession, right? So the sky level doesn't vary much between.
Yeah, well, for those supernova ones, they were, that's over the course of many days, but it just happens that that first and last image were pretty much the same level. So it worked out with that particular data set. Yeah, and since I was going with an archival data set anyway, again, I wrote the lab back in 2008 when we didn't have a plethora that we could choose from, like we were just discussing. So I figured it is going to be this set, and it just happened, we were using a movie to identify the source. So I just checked it over the summer, and I was just fortunate that the first and last one, actually I removed the first image. It was the second and last one that had the same levels, so I could do the subtraction and calibration. I tweaked it a little bit.
Right.
So Dan, when you all discover these supernova in the southern hemisphere, there's some sort of pipeline that generates images that are already calibrated and so on?
Yeah, that's external to us. It's the DLT 40 team, David Sand at Arizona and Stefano Valenti at UC Davis. And they're the ones we also partner with to do the gravitational wave stuff. And your telescope, as well, when we have a gravitational wave event, they will be taking over control of all the Skynet telescopes. Sending some telescopes to this galaxy, some telescopes to that galaxy. And so your data will go through their pipeline for gravitational wave events.
So you could presumably have them send a calibrated pictures of supernovae via some criterion. Maybe it has to be outside the galaxy or something, and then just queue them up, and then the students could have access to them.
Yeah, that's right. Instead of using the one that we're using now, first of all, we could calibrate the one we're using now, replace those images with calibrated images. That's also a good idea that I'm going to write down. It doesn't matter for this, just by chance, it doesn't matter, but it'd be nicer if they were calibrated images. But yeah, we could partner with them, and whenever they have one that meets certain criteria, we could put it somewhere, maybe automatically put it in the sample directory. And so they can take the most recent one, kind of like with the asteroid observations before you all had the capability of getting the parallax data yourself. We'd put them there and people would use the most recent ones. Maybe we can automate that. I do like that idea. It's in the sample directory anyway. As long as they meet the criteria, it should work in theory. And if it doesn't, they can go back and try a different one. I think that's really good. And then it feels more real. Like this is coming in off these telescopes real time. Here's one a couple days old. Here's one a week old. Yeah. I'll talk to them about that.
Yeah, the students can kind of feel like they're part of the Supernova team.
Yeah. I think that's a great idea. It'd be a little bit extra work, but you know, it won't require hardly any change to the directions of the lab. Like one sentence change. It requires some work behind the scenes, but we have programmers, and because the grants, they're fully paid now, so they have, this is the kind of stuff they're supposed to be doing. Yeah. And we already have this great relationship with DLT40. We work intimately close on the gravitational wave stuff. They're using our API to communicate back. So this should be doable. I like it. Other thoughts? I think it's a nice, clean lab. Again, I like the repetition part of it. I think the background sections give them just enough for a survey level student. And you'll see next week when we do the great debate, it sets them up for that. 5 and 6 kind of go together nicely. All right, well, if there's nothing else, I'll let you go and we'll meet up again next time.
Great.
Thank you, Dan.
Thank you.
Thanks.
Take care, Dan.
Yep.
And everybody else.
Bye.
You too. Bye.